All right, so first of all, good afternoon, everyone. My name is Skanda, and I'm the treasurer of the topical group on data science, GDS. And thank you so much for being here. So GDS is a new topical group, and it was started in 2018, thanks to the leadership of Mohammed and Gia. And so basically, there are many exciting overlaps between physics and data science. AI has been recently making an impact in fundamental new physics discoveries, as well as data science has its roots in physics in terms of methodology and optimizing large data sets. So that's the background behind why we were all excited to start this topical group. And so basically, in light of the March meeting being canceled, we've organized a set of invited talks as well as tutorials, and in the upcoming near future, we would also have all of the sessions from the March meeting so that speakers can present. So first of all, we have two very exciting talks today from Devin Silvia, as well as Trever Rhone. And Alexis will tell us a little bit about the speakers in a bit. So these are some of the past webinars. Last week, we had our first webinar where Patrick Riley, Rama Vasudevan, and Sarah Stone all give very exciting talks. And we also have some exciting upcoming talks. So just stay tuned for that. In fact, the soonest talk is actually at 3 p.m. today, so we definitely need to make sure that we finish before that, but I don't think we'll have a problem. And that would be the GDS short course on deep learning for image processing applications. So very cool, cutting edge stuff. We also have on Tuesday, the GDS short course on deep learning for image processing. And then all of you who sign up, and you'll also get a link soon, will be provided more details about this. And there are some more upcoming webinar events. So I suggest all of you to keep posted about this, and if share it also in future when the links arrive. Okay. All right, so now I'm going to give it over to Alexis to talk about, give a little bit of an introduction to our first speaker, Devin Silvia. Alexis.
Thank you. Our first speaker is Devin Silvia. He is the Director of Undergraduate Studies for the Department of Computational Mathematics, Science, and Engineering at Michigan State University. He's currently leading CMSE's efforts to roll out a new bachelor's degree in data science in the College of Natural Science, and is the primary advisor for students within the new program. Students first started enrolling in the major during fall of 2019, and MSU plans to graduate its first cohort of data science students in spring of 2022. Devin's background is in computational astrophysics with a focus on understanding how the gas between and around galaxies evolve as a function of time. He is also leading new research efforts in computational science education at Michigan State. And let's see, his, and let's bring in is the screen up.
All right.
So just 1 minute before that starts, well, all of you who are attending, please free to provide questions if you in the chat window, as well as you can raise your hands and we can answer your question after the speaker speaks. Thank you. And Devin, please go ahead.
Great. Thank you, Alexis. Oh, hang on. Can everyone see the screen? Hopefully. Thank you, Alexis, for the introduction. Thank you for the organizers putting this together and finding a good way to recover from the unfortunate cancellation of the original meeting. I'm excited to present today. And so hopefully, if we have any questions, we can address those at the end, and hopefully the facilitators here will help me figure that out, because I don't know if I can see them, but we'll go ahead and get started. So what I wanted to talk today about is some of the research that we've done here at Michigan State in what is a relatively new department. It's only about 5 years old, Department of Computational Math, Science, and Engineering, and talk about how that research is allowing us to inform the curriculum design choices that we're making for our new bachelor's degree in data science. As Alexis said, We, as of this fall of this academic year, we have a degree. We have about 40 declared majors, and that's with very little advertising on our part. We're hoping for a incoming class of about 50 per year, and so we're sort of in the ramp up and development phase for that, which requires designing some new courses and thinking about our major level learning goals as well as a course by course basis. And so what I'm going to present today is a little bit of research we did to try to prepare for that that rollout. Okay. I'd like to spend a little bit of time talking about what CMSE is, because we are such a new and young department that Michigan State is investing in. There we go. So what is CMSE? This is our logo, which I feel the need to explain from time to time. We are, all of the words associated with this mouthful is Department of Computational Mathematics, Science, and Engineering. And this department was really designed to be interdisciplinary from the beginning. And so we have various versions of our logo that sort of have these three intersecting circles. And that was really something that came out of the initial design of the department. One version, because we have many of them at this point, highlights some of the ways that we like to think about the department. And really, we want to be sort of the intersection between traditional computer science, high performance computing, current programming techniques, but then also disciplinary modeling. And so that can be engineering, physics, chemistry, biology, whatever it is that has some reason to be doing computational work, and creating a space for people to do that. And then, of course, wrapped into that, we also work with applied mathematicians, algorithm development, and things like that to bring in new and current theories as to how best solve these types of problems. But something that often follows up, well, yes, you can tell me what this department is and why it was created, but why did you do it in the first place? And the motivation is really that we found, at least at Michigan State, and this may not be true at every institution, was that we had many people on campus. We're a large campus. We have 50,000 undergrads. We have many, many researchers who do computational work in their day-to-day lives, but we didn't really have any sort of cohesive place for those faculty members, those postdoctoral researchers, whoever that is that's doing that work, to really sort of get together and talk about their techniques and their ideas and build collaborations. And so MSU decided to put everyone in one place and as much as possible. And so many of the people that are in CMSE have joint appointments, so that they can basically work side by side with chemists, physicists, electrical engineers, mechanical engineers. Anyone who's doing computational work now has a place to go and be a part of a community that's all doing these sorts of things. And it really grew out of the fact that the computer science department here, which is doing good things, couldn't do all of that on its own. And so we now have this new department, and it grew out of people coming from applied math, statistics, computational physics, and CS. So we're really trying to be something new and different, and we'll see how things go over the next few years. But so far, it's been a really fun place to work. One of the aspects that also motivated the creation of CMSE is trying to figure out a way to teach computation in an applied way outside of a traditional computer science classroom. So what we were seeing on campus was that students were self-identifying as having a career need to learn to do computational work, but they weren't actually getting the skills they were looking for when they took a traditional computer science course. So many of them were taking the Intro to Programming course offered by our CS department and really weren't having a great time in there, because it's really geared toward people who want to be computer science folks, people who want to be software developers. And so if you're a biologist who just wants to learn how to code to analyze your biology data, that's not necessarily the right place for you to be. And the CS department just doesn't have the capacity to teach sort of these applied ways of doing programming. So that was sort of our motivation, our goal, and it manifested in our first undergraduate course that was ever taught as part of CMSE, a course we call CMSE 201, which is Intro to Computational Modeling and Data Analysis. And hopefully, if I can get through the content that I have planned for today, we can talk a little bit about the design and thoughts that go in to that course. I also attended the International Conference on Computational Science last summer, and there's a full write-up about the design choices we made for CMSE 201 and how we expect students to be learning from that. Okay. So hopefully, if there's time at the end, we'll go through a bit of that. But what I want to do first is talk about the qualitative education research we did to really try to understand what do experts in computational and data science say that their employees need to be able to do. So if we have a new bachelor's degree program, we want students to be successful when they leave our campus, or we want them to be successful during their internships or research opportunities here on campus. What are the things that we need to be integrating into our curriculum? And can we do this from an informed research perspective rather than sort of gut intuition and things like that? So I'm going to present some of that work. This work is culminated in 2 papers that we're hoping to get published in the next month or 2. The first of which is a paper that really just gives an overview of the sort of takeaway messages we got from the interviews, what were the main themes that emerged from that interview study. And then the second paper is a follow-up that looks at some of the nuance between what happens when we're talking to experts within academia versus experts in industry. So that is all forthcoming. One of the challenges we've run into a little bit is that because this work is not sort of traditional computer science education research, finding the right journal and the right audience has been a little bit harder than we originally envisioned. And so we've got some ideas in mind, and we're making some final tweaks to really make sure that this is pitched in the right way. So keep an eye out for those. Hopefully those will come out. That work was led by a now graduate student in the Department of CMSC here at MSU, who's now doing some bioinformatics research. So the big research question, what are the key competencies and skills needed by undergraduate students in order to be successful in their future careers as data scientists and computational professionals? And so that's really what is going to inform the way in which we build the themes that show up in our qualitative interview data, and really what motivated the design of our interviews and things like that. So a little bit about the methods that we employed. Okay, so as I said, the goal here was to try to build an expert model of what it means to be a successful computational or data scientist. And so we're sort of using this expert novice theoretical framework, which is pretty self-describing. You basically use what you can learn from the experts in order to build what you should be teaching the novices. And that's kind of the way that we pitched this. We did this through a series of semi-structured interviews. Okay, so we basically came up with a set of questions that we asked every interviewee, but we allowed ourselves enough flexibility that if we needed to pivot or to a slightly different direction, we had that space to do so. And then also if there was an interesting thread, we could kind of pull at it in real time, but still collect the same data from everyone by making sure everyone still got the same base level set of questions. Once we had all the data in hand, we went through a thematic analysis where we let sort of the data, we went through and we code the data and figure out from there, based on what we're hearing in the interviews, what are the main themes that come out from that data set, okay? How did we actually select our interviewees? We wanted to make sure we pulled from both professionals in industry and academia, since we envision that we'll have students that are pursuing both paths. So we wanted to have expert opinions from both categories. So we actually sort of identified the types of people that we thought would be good fits. So people working in academia, people working in industry, people who are regularly hiring undergraduate students, or working and leading teams that work with recent graduates or current undergraduates in internship settings. We then sent all the people we identified as potential candidates a pre-survey where we asked a few basic questions to try to make sure that they were a good fit to be able to share those those expert perspectives that we were looking for. And we in the end ended up with a set of 18 interviewees, half of which came from academia, and half of which came from industry. And I will say that actually the hardest part about collecting this data was finding people from industry who were willing to make the time to sit down and have sort of an hour-long interview with us when they don't really get anything meaningful out of it. So that was an interesting challenge that I was not prepared for, but it actually took a while to create that set of 9 industry interviewees. So if you proceed down this path, know that that may be an obstacle you run into. The way that we collect the data, so we actually conducted a pilot interview with one of our interviewees, ran our interview protocol, the questions that we had pre-designed, and sort of just made sure that the protocol elicited the information we were hoping for. So we conducted that interview, transcribed it, and then sort of looked at it to say, is this creating the types of things we were hoping to see? Once we were sure that the interview protocol worked just the way we wanted to, then we conducted the rest of our interviews. There's this fun transcription phase in there, which thankfully Nat Hawkins took care of for us. He spent a lot of time transcribing things because he wanted to make sure that he had a good understanding of the data. There are services you can use for this type of thing, but he did it by hand. Then he went through all of the information that comes out of those transcripts, codes them, so basically identifies interesting pieces of the conversation that look like they might represent meaningful data based on what our research question was. That creates a final set of quotes that then we sort of filter and sort in order to create our main themes. So I just want to give people a little bit of background about what that interview process is like for those of you that don't necessarily do qualitative education research. It is kind of a time-intensive process. Even though we only did 18 interviews, it's a lot of data to work with. And now, of course, there may be technological advantages down the road that we could leverage to sort of mine this data automatically, but it really does require a bit of careful oversight and nuance. So what did we get out of that? What are the major takeaway themes? The main themes that aligned with the question we're asking, which is really looking for skills, competencies, and knowledge that our students should have, were perhaps unsurprising to some degree. And I should point out that we did look at the literature to see what was out there before we went through this. We did want to carry out the study for the benefit of CMSC, but we also wanted to see how it would fit within the greater community. And while there is work out there trying to understand some of the similar things, they're often done by sort of consensus building within a somewhat limited group of individuals. So we wanted a diversity of perspectives, and we wanted to be sort of methodical and really take a research bent on this. And so coming out of that, you have computational skills, interpersonal or people skills, abstract skills, and depth of knowledge. And I'm going to break into show you what some of the data looks like for computational skills and interpersonal skills. Abstract skills would be things like problem solving, critical thinking, those types of things, which can be really challenging to assess. And then depth of knowledge is really just thinking about what sort of either domain expertise is needed, what sort of technical skills are needed, really thinking about like how far along in your education do you need to be to work in this particular discipline, or what is the core set of courses you would have to get through in order to get there and be successful. Again, these aren't necessarily surprising, but we do now have a data set that really supports that these are critical themes that are coming up for people that are trying to be successful. So as I said, I want to spend a little bit of time showing what some of the data looks like on the computational skills and interpersonal skills front. So once we had our main themes, within that, based on the data that we have available, there are sub-themes that come out of it. So the sub-themes are things like machine learning, working with data, visualizing your results, traditional computer science type skills, the ability to debug and troubleshoot comes up quite a bit. What is your mentality when working with code? How do you approach that type of thing? And so these are things that come out when the interviewees were talking about the computational skills they look for. And so what I want to do is give some examples that come from the machine learning perspective. I'm going to pause that for a second. You're going to see a big quote. I've highlighted some of the critical text that sort of indicates why we coded it for a particular sub-theme. And then I'm going to try to provide examples from industry and academia. So this first quote here is a big one. There's a lot of technical stuff in there. This is actually coming from industry. That's what the I indicates. So Gary from industry is talking about students need to understand what features are, broadly speaking. They need to understand when they should and should not add new features, understanding the difference between classification, regression, various machine learning techniques. You can see a lot of technical jargon in there. So this very clearly would code the importance of this machine learning computational expertise. But then you have someone like Dennis from academia who says they should know scikit-learn. They should know what machine learning is and how it works. So very different ends of the spectrum as far as where they're coming at. And some of that comes from the fact that in some cases, faculty in academia are sort of working with people they know yet aren't all the way to the graduation point. So they might be hiring someone for a summer research project or during semester part-time research. And so where they're looking that person to come at into their research group might be different than someone who's hiring someone to be a full-time data scientist at a company. So there is some differences in those populations that do come out. When we think about sort of data science or working with data specifically, we have Armin from industry is talking about we need people that can work with large amounts of data. We have to have familiarity with huge parallel distributed networks, sometimes utilizing GPUs. So you're seeing that this is really the big data realm that somebody is working in versus Diana from academia, who works in a different discipline. And she's sort of saying, I don't do big data calculations. I work with small CSV files you can read on your laptop, but they're complex and they still require some of the modern data analysis and data science techniques they're just not at the same scale. So I don't need you to know how to work on remote machines or use parallel algorithms. And so you, again, have differences. And these differences vary between industry and academia, and even from one industry person to another. Some examples, what are we talking about when we say interpersonal skills or people skills? Sometimes you often hear this referred to as soft skills. And these are things like communication, collaboration, mentoring, professionalism, social interaction. And the mentoring one is an interesting one that came out of the data. Is sometimes what that's referring to is people want to hire individuals who are capable of being mentored, but then also people who are capable of mentoring others. And so depending on where they're at in their career might be a slightly different way, but they're still talking about mentoring as being a critical part of being successful within that group. And so what are some of these examples look like? From the communication perspective, we see things along the lines of, we need people to be able to give an hour-long presentation, communicate ideas effectively, okay? Related to that, Hamilton from academia, you need to be able to show that you're an authority and you have a command of that topic. And anyone who works within academia probably has a sense that, like, we're doing this all the time. We're giving talks like I am right now, where you're basically trying to communicate your results and convince someone that you know what you're talking about. And they need people that can do that. That does come up in industry as well, depending on the context. You might even have to be able to make that case to someone who's a non-expert. And can you do that as well as you can do it with experts? And that can become important. From a collaboration perspective, you sort of have different things that come up. Jamie from academia talks about people being able to work independently, but then be facilitated by others. So if you're working on a project independently that you're the lead on, you might need to work with someone who has the expertise you don't have and be able to sort of be productive where they can kind of guide you in their knowledge, and then you can integrate that to make forward progress. Armin from industry says, you know, we're no longer in the time of working in siloed spaces in our own offices where we just get to hammer away on whatever our pet project is. But now we have to have a lot of face-to-face time with fellow members. You've got to be able to work with the people around you. And every interviewee we talked to eventually ended up talking about the importance of having productive, collaborative group members. And so if we aren't integrating the opportunities to collaborate into our curricula, we're really doing these students a disservice, because they're going to go out into the real world and be expected to do things and be expected to be good at doing them, okay? So we could go and we could look at the data all day. We have a lot of different quotes and really some nice gems that come out of that. But we also wanted to understand if there's significant differences between industry and academia. Are they looking for different things on average? And so one of the ways that we tried to look at this is just look at sort of the frequency of quotes talking about different things. What fraction of the overall quotes that we used from different interviews ended up highlighting one topic versus another? How did that break down between the two disciplines? And so the way that we've tried to think a little bit about this, and this is a slightly modified version of one of our earlier figures, but blue indicates that it's comments and quotes that are coming from industry for particular subthemes, versus red is things coming from academia. And you can sort of get a sense that when, for example, I look at computational skills, the industry individuals we talk to really emphasize a little bit more about technical expertise. So do they have specific machine learning skills? Do they know how to work with data, whether it's big data or small data? Whereas sometimes in the academic realm, we're looking at more like, what do they do when they run into a bug? Do they know how to troubleshoot problems so that I don't have to monitor them constantly? And it's interesting just in talking about, with folks, how these different things came up. When you think about the interpersonal skills side of things, many of our industry interviews talked about the importance of mentoring, whether that's being mentored or mentoring others. In academia, we do a lot of mentoring, but it didn't come up in quite the same way. And so social interaction, like how do you work with other people? How do you interact with other people? You know, are you thoughtful? Are you do you respect your collaborators? Things like that, interesting differences. And so we're still digging into some of this nuance and trying to understand exactly what this tells us. From the abstract perspective, one of the things that came up time and time again in our academic interviews is the importance of grit. And I think those of you that have worked within academia understand probably a bit about what that means and where that's coming from. So we have all this data, we have these papers we're hoping to publish this year. What are we doing with this information? How are we using it here at Michigan State in the Department of Computational Math Science and Engineering? Well, the nice thing is much of the data that came out of that does verify that the content we're teaching in our 200 level courses is well aligned with what experts are looking for. And that's not necessarily by accident. You know, we did a lot of informal conversations when we started designing these courses. We just weren't collecting and analyzing the data the way that we have now. So that's not necessarily surprising, but it does identify areas of our curriculum that need further development. So in our 200 level courses, we can't dig heavily into machine learning techniques, but we know that given the way that the world is working and the way that we're progressing towards more and more prevalent machine learning, we do need to understand how to integrate that into the 300 and 400 level courses and make sure that we're touching on the right topics that are currently relevant and be aware that those will evolve as a function of time. So going beyond the scope of our introductory courses, we're going to have to think about our higher level courses. And it does provide us with data to rationalize the decisions that we're making about the data science degree program. So as I said, we started the program this fall. We're actually going to teach some of our 300 level courses for the first time this coming academic year. So we need to be thinking about what do we put in those and how can we use this data to inform it. And then also, what's the vertical arc to our undergraduate degree program? How do we make sure that integrated to every step of the way are opportunities to collaborate, opportunities to communicate and work with others? And so it really does help us shape the decisions that we're making here at Michigan State. What's next, though? Where do we go from here? We'd like to gather more data. So I should point out that the academic interviews we have, mainly out of limited time and sort of resources to reach out to institutions across the country. We stayed here at home at Michigan State. So we do think that our interviews that come from academia are representative of big universities, so large research universities like Michigan State, but we may want to try to collect interview from different types of institutions to make sure that we're still getting consistent results. As I pointed out, there's a lot of nuance in the data. It might be worth finding some of these things and digging in with new follow-up interviews where we try to dig in a little bit further about maybe some of these interpersonal skills and how they actually play out in the workplace, or maybe we need more information about exactly at what level do students need to have some of these computational skills. So plenty of opportunity for follow-up interview. We're also hoping to observe and interview students to see how they engage with these various themes. So how are they thinking about the importance of collaboration? Do they realize they're collaborating when we design courses that are group-driven? How are they sort of internalizing that information? And then ultimately design assessments so that we know we're accomplishing the things that we set out to do. What I do want to do now, I think in the time that I have left, is move on to a brief overview of the CMSD 201 course that we've taught, which is really sort of the entry point into the data science degree program. It's also the course that is being widely used in sort of as the foundation for a physics program or a biochemistry program. New programs are thinking about adding it. So what does this course look like? How did we design it? And that's where I'll sort of wrap up today. I'll just walk through quickly. So the high level learning goals, we want students to be able to learn about the systems they're observing through computational algorithms and tools. Perhaps that's not surprising. That's generally what we're all trying to accomplish, I think, in the work that we do that's computational. But we want to make that explicit to the students. We also want to make sure they learn to program. So this really is thought of as an intro programming course. So they're learning Python for the first time, and we have to think about what that means and how they do it. But while they're learning to program, we want to make sure they're solving problems. We don't want them to write code for the sake of writing code. We want it to be in as many different disciplines as possible, which can provide its own challenges. We want to be able to identify students to be able to identify salient features of a system and turn it into code. So how do you go from a mathematical representation into a code representation? How do you make an observation of the real world and turn that into a agent-based model that you can do interesting analysis with? Or what are the parts of the system that define the way your model works that then you're going to need to understand when you analyze your data? So all of that is things that we're trying to cover and teach. How do you actually manipulate, analyze, visualize data? So we do have them working with data on a regular basis and trying to get them to ask meaningful questions and then answer it using their data. Of course, we want to teach them basic numerical methods. So we teach things like numerical solutions to differential equations. We talk about regression analysis, things like that, traditional methods that we sort of, again, apply to solve problems. And then finally, and this is something that we were already doing before we had all this interview data, is present it both verbally and in writing. And so we want students to be able to actually communicate the work that they're doing, and there's multiple opportunities throughout this course for them to do that. For the sake of time, I'm going to skip past this a little bit quickly, but I do want to highlight, so much of our design choices were informed by this book, How Learning Works, which is really useful to think about how at the undergraduate level, we should be thinking about the learning process and how do we design our courses with those learning principles in mind. So one of the ones I want to highlight and that we tried to sort of we used a lot to design our course is this idea that in order to actually become masters in some particular thing and have mastery over that, students need to acquire component skills, practice integrating, and practice multiple times while getting feedback, and then know how to apply that to new scenarios. Okay, and so that's a lot of what we're trying to do as we design this course. I'm going to skip past some of these other ones. And what I want to show is sort of the initial few days of the progression of this course to see how we sort of try to thread together modeling and sort of data analysis, data science concepts. We try to give real world context as much as possible. And then we are trying to sort of gradually introduce programming techniques. So I'm going to put up a table that there's a lot of information in. So apologies for that. But sort of the three columns are the three main threads we've used in designing this course. Talking about some sort of modeling techniques. So at the very beginning of the semester, we talk about making estimates, doing sort of back of the envelope or order of magnitude calculations, which is a nice entry point into programming because you can just sort of define some variables, manipulate them, multiply them together, do simple math, some of the basics like just writing code and seeing what it does, gets them up and running pretty quickly. And we can apply that to a variety of contexts, whether it's sort of estimating the amount of toilet paper one might go through, which is perhaps particularly relevant right now, to understanding the capacity of the Breslin Center when there's a game going on and various things like that. So we can have them do those types of interesting problems. And as we work through, we get them, you can see by the last row here, we're actually having them load, read data, make plots of it. And so this is where we actually start introducing the idea of correlation and what does that mean and how do you extract information from data in meaningful ways. And so again, every time they learn a new programming technique, they're applying it to a particular context with some sort of data analysis or modeling technique wrapped into it. So how do we actually implement this? In the time I have left, I'll just kind of flip through some of these things. Our computational platform, we do everything through Jupyter Notebooks, which has been a really great way to design curriculum for us. There are some limitations, but it really allows someone to integrate narrative text that sort of explains what the students are doing, why they're doing it, along with example code or space for them to write and test their own code. So the sort of as a communication platform integrated with computation, it's really, really quite powerful. I'm sure many of you have used them before. We also teach this course as a flipped classroom. So much of what we're doing is students do some sort of pre-assigned reading, watching of videos, basically learning a bit of the content and context before they come into the classroom. Then during the classroom, much of what they're doing is working in groups and collaboratively trying to develop code and solve problems. How do we facilitate this? Physical space is really important, which I'm really beginning to appreciate now that we're teaching all online courses. But the physical space really does help drive the interactions. And I've actually been able to translate much of that over, but what does it look like here at MSU? At MSU, we have what are called real classrooms, which I think is a bit of a confusing and short-sighted name, but basically they're classrooms that are meant to be active and engaged. And so you see that it's group tables set up with students literally facing each other to be able to talk and have conversations. There's no one to lecture from, so it discourages that behavior.
Wanted to let you know that we're almost out of time.
Okay, great, thank you. And so if that doesn't work, you can just slap together some tables, give them a little bit of whiteboard, and you can achieve the same thing even if you don't have those resources. This is an example of students working in the classroom in both contexts. I want to highlight the instructor is just embedded in there, bouncing between tables, interacting with students in real time. I've been doing largely that through Zoom breakout rooms now. And we try to keep the instructor to the student ratio as low as possible. So we do that through undergraduate learning assistants and TAs. So of course, by the end of the semester, have we actually proven that students can choose, design, implement a project on their own, and importantly, communicate the results? So the way that we set that up, around the middle of the semester, students start thinking about their semester projects that they will present at the end of the semester. One example of a final project notebook looks something like this, and this was actually from a couple of semesters ago, so despite the title, it was not relevant to right now. I already happen to have this slide prepared, but this student really wanted to understand the nature of flu and pneumonia-related deaths in the United States. And so you can see the student has set up their background motivation, they go into their methodology, they present their results, and then they sort of have a wrap-up discussion. How has this course evolved? Challenges, lessons learned. It's resource intensive. So we have to have enough learning assistants for this group-driven interaction, facilitate this style of learning. Making sure that all the students can install Python and run Jupyter Notebooks is important. We also have a cloud-based Jupyter Hub server to make sure students can use that when their laptops fail. So there is a lot to make it happen, but we've been successful at doing that so far. Scaling can be a challenge. When we started the course, we had about 20 student sections. Now we have 80 student sections. We have over 400 students that are enrolling this fall. We started with 30. So in 2016. So things are growing quickly, and we're trying to find ways to scale this up. And then interdisciplinary content's a challenge. My background's computational astrophysics, but I want to have social science models. I want to have biological models. So I do my best to integrate that. And demand is high. We're constantly being asked by other departments if they can use this as a prereq for a certain course or as a component of their major. So we're trying to figure out how to do that and support that. So I'll stop there for questions.
Thank you so much, Devin. So if anybody has any questions, they could put it in the chat window or raise your hand. I can unmute you.
Can I see this?
You can also type the question into the question tab. That you may not be able to use the chat if you're just an attendee. Thanks.
Go ahead, Jerry. I've unmuted you. I see somebody unmuted. Let's see. Okay, let me just answer that, ask that question. So Jenny asks, how do you deal with the different preparation levels for your classes?
That's a great question. So when we first started teaching the courses, we were fortunate enough that it was an elective for most students, and so they were self-selecting and all coming in with a pretty driven and with a little bit of experience already. But now, as the course has evolved, we have students that come in as first-year students, and we also have occasionally still third and fourth-year students. The way that we've supported students at different backgrounds is we have the same way that we leverage learning assistants in the classroom to help facilitate. Those learning assistants offer a lot of outside that classroom help. So they offer, every learning assistant has about 2 hours of help room a week, which right now for our CMSE 201 course, between the PhD level instructors, the grad students, and the undergraduate learning assistants, we have about 30 hours a week of help room. That's where a lot of those less prepared students end up, and we're able to sort of give them enough one-on-one time to support that progress and that development. So we generally are able to lift up those students that maybe have never written code before, but it's designed to be an intro course where we don't assume any prior knowledge. We also design our assignments to have sort of challenge exercises at the end for students that are more advanced to keep them engaged and push them further.
There's another question coming in. How large is this new department and who are the faculty? Are they professors from MSU departments?
Yes, so the department right now, I think we have about 32 full-time equivalent positions, something like that. The faculty in CMSE, almost all of them have joint appointments. Those appointments are often either 70% CMSE or 70% another department, so they have majority minority appointments. The place that they report to is wherever their majority appointment is. But really, the model, MSU actually is very into this model of joint appointments. So many faculty on campus have joint appointments across departments. With the exception of about 3 faculty, I think everyone is jointly appointed in at least 2 departments. Some people are across 4, which causes logistical nightmares for some folks. But those faculty come from electrical engineering, mechanical engineering, material science, chemistry, biology. We have people from medical disciplines, physics, applied math, pure math, really quite diverse. So it's a little bit of everything. We have been hiring at a rate of 1 to 3 new faculty per year, and we're hoping to continue that for the next few years or so. We're hoping for a final count of about 50 faculty in the department.
All right, thank you so much. So in the interest of time, let's move on to the next speaker. Before that, I put, there's a poll that's out there, which is about how did you hear about this webinar? I'm also going to launch the poll, and I think that you could answer it when you can, everybody who's attending this webinar. So Alexis, would you mind introducing our next speaker, please? Trevor, thank you.
1 second. So our next speaker, let me turn on my video because that's kind of weird. Our next speaker is Trever David Rhone. He received a liberal arts education from Macalester College in St. Paul. He went on to pursue his doctoral studies at Columbia University in the city of New York, where he did experimental studies of two-dimensional electron systems in the extreme quantum limit. Trever David spent several years at NTT Basic Research Laboratories in Japan. During this time, he transitioned to materials informatics research, exploring machine learning tools to perform materials research. He continued this work at Harvard University, where he used machine learning to search for new 2D magnetic materials. Trever David Rhone's research interests include using machine learning tools for materials discovery and knowledge discovery. Materials discovery could manifest in the search for new 2D materials with exotic properties, the prediction of the outcome of industrially relevant catalytic reactions, for other compelling research problems. In addition, data analytics tools will be used to aid in developing a better understanding of physical systems. And I will give it over to Trever David. He should be sharing. Let's see.
Is Trevor here?
Looks like we lost Trevor.
We lost Trevor.
Someone muted me, so I had to unmute myself. Hello.
No problem. Thank you. And now it's your turn.
Great. Thank you for the introduction. My name is Trever David Rhone, and currently I'm a professor at RPI, where we're quite keen on using data science for physics research. And the title of my talk is A Beginner's Guide to Using Data Science for Physicists.
Trevor, can you share your screen?
Okay. Can you see my screen now?
Perfect, thanks.
Okay, thank you. So the title of the talk is Beginner's Guide to Using Data Science for Physicists. And the story begins in 2012. I'm at Columbia as a grad student doing experiments in light scattering. And I understand from the news that data science is becoming more and more important in the world. And I got interested in using data science to tackle problems in physics. But I had no idea where to go, what to do, or how to get started. And so it took me several years to kind of figure out the path towards using data science in research. I didn't know of anyone else doing something similar for physics at the same time. And this talk is hopefully a guide for you to help you get started faster and to do data science research in your area of choice much more quickly. So with any introductory talk, I like beginning it with the following poem by Rudyard Kipling. It's, "I keep 6 honest serving men. They taught me all I knew. Their names were what and why and when and how and where and who." So let's begin the talk with what is data science. It is a combination of different areas of research, of study, computer science, statistics, combined with some knowledge base through digital data. It's very interdisciplinary, combining areas of statistics, databases, data mining, and data visualization. It has a lot of overlap with area of machine learning and, of course, AI or artificial intelligence. Why do we care about data science? Well, about when I heard about it, became interested in myself, there was a lot of interest in targeted advertisements through companies like Facebook or Amazon or Google. And of course, maybe closer to home and quite relevant these days, Netflix movie recommendations. And then at some point, the self-driving cars became quite relevant and a topic of discussion. And more recently, in the last 5 years or so, physicists, condensed matter physicists, are using materials discovery, data science to do materials discovery. And the problem is experiments can be slow, calculations can be also slow and expensive. And in cases where there's no analytical solution, it's useful to have another approach to help solve problems in materials research. And not only for discovering new materials, but also to uncover new physical insights in the study of these materials. Now, the when and the where of data science. This picture is of Thales of Miletus in ancient Greece. He is the first person known to be a data scientist or to have used data science. He lived in around 600 BC. And the story goes that Thales became maybe one of the first scientists, became keen on studying data. He studied the weather patterns. And after some time, he realized that he could predict how good the upcoming orchard, or rather olive crop would be. And so after studying the data of the olive farming, he found that the following year there would be quite a good olive crop. So even though he was a philosopher, and philosophers weren't known for making a lot of money, he rented many olive presses, and the following year when the olive crop was quite good, everyone had to go through him. So through this scheme, he made quite a bit of money, despite him being a philosopher. After Thales, many years after, data science was used in areas which are familiar to you, like observational astronomy, bioinformatics, of course, social media and targeted advertising. Indeed, we're in the era of big data, where data are accessible and data analytics tools are readily available, making these tools and ability to exploit data accessible to people like us who are necessarily computer scientists or statisticians. How do we do data science? Well, I present here the essential guide of doing data science. That is, first you need to get data available through places like Kaggle. Kaggle is a place where they hold data science competitions, and you can have easily accessible and free amounts of freely available data of various types and sources. And also recently, Google has launched a dataset search tool where you can Google the dataset you want and you typically get the CSV file back, which is very useful. Over on the right is a picture of some homes in Copenhagen. And this is important because typically once you have some data, it could be for housing prices, you want to have a good descriptor, which is often a mathematical representation of those data built on some domain knowledge. And for the sake of example, in the case of housing prices, you might imagine a good descriptor might be the area of the house or number of rooms or number of bathrooms, number of windows, for instance, but not something like the color of the home, for example. So once you have lots of data and descriptors with which to describe the data, you can typically do data visualization afterwards. It gives you some intuition about how the data might work or behave. And then at some point you do model selection. You pick based on the question you're trying to answer what model might be useful for you. And then after that, the step is to do model validation, where there's schemes for figuring out whether the model really captures underlying behavior of the system you're trying to study. And after the model is built and it behaves well, you do the model exploitation stage, which is to make some nice predictions and take advantage of all the predictions and new knowledge that you've gained from building the model. the really nice thing nowadays is that a data science ecosystem exists where you can store data, transform data, and model data, visualize data really easily with tools that are already available and are easy to use. So for instance, if you want to store data, there are tools exist like MongoDB, which can help you to do that. To transform data into some useful things, to, for instance, build models, you can use Python, which is free and very powerful. To model the data, build models that could be used to do regressions or classifications. There are Python packages like scikit-learn, which are available. Then once you have your very nice models, what you can do next is use free software like matplotlib to visualize those very nice predictions. So really, the tools exist and data exists, so it's really nice time to be a data scientist. Data science, as I alluded to before, is a combination of data visualization and machine learning, where the goal is to take your machine learning model, which approximates some function f of x, shown here, where your observed data, y, or target property, y, is coming from some underlying behavior plus some error in the measurement. Now, keep in mind here that I have x1, x2 through xn, where n can grow very large. And the key advantage of data science is that you can make sense or look for patterns in high dimensional data. In the case of housing prices, you might imagine there are a few things that could be interesting or relevant to predicting the housing price, like the number of rooms or the area, and you can kind of make sense of this. But what if the number of features or descriptors were not just 2, but 100? It's then quite difficult for a human to gain intuition into how all these descriptors work towards predicting a certain value like y, but it's easy for a machine to be able to do that. So the goal here is to learn or quantify some key relationship. So we can ask yourself the questions, what are good descriptors, and then visualize those descriptors in some way. An example of that is the following, again for housing prices, where I'm plotting on the x-axis the constructed area, and on the y-axis the housing price. And these are different homes. Each point represents a home. And you find that indeed the area seems to be correlated with the housing price, so it's a good descriptor to hopefully build a model to predict the housing price. We can kind of iterate through this idea by guessing another descriptor. It could be the number of windows, or it could be the color of the home, and making this kind of visualization, getting a sense of what the good descriptors might be. And of course, there are other systematic tools with which one can use to develop descriptors. And actually, the area of building descriptors is an active area of research. So in machine learning, you can say there are general classes of models, and roughly speaking, I would describe 2. There are more than 2, but let's say there's supervised and unsupervised learning models. And for the supervised case, that just means that in your parameter space of 2, here x1 and x2, your data come labeled. So they're, in this case, blue circles and red crosses. And if you want to, say, predict what some new data is, you can build a decision boundary that's shown here, and some new point, let's say it falls somewhere here. You can say, well, it's unlabeled in this case. You'd say, if it falls to the left of my decision boundary, it must be a blue circle. And if it's falling to the right of my decision boundary, it must be a red cross. And the advantage of this is if each point takes, say, some months or several days to measure, having some new unlabeled point and a machine learning model, you can very easily, very quickly, in milliseconds, kind of guess what the label should be. So that's supervised learning. There's also unsupervised learning, which is you have some completely unlabeled data, and you notice some pattern in the data. You notice that there are clusters that form. And if you do that, you can identify these clusters very clearly. And upon further investigation, you might notice some common characteristic of each cluster. For instance, in this case, each cluster shares the same color. It could be for application in housing prices. It could be each house shares the same zip code, or for an application in physics, it could be each has the same element in each cluster. So just diving a little bit more deeper into statistical models and focusing on, for the rest of the talk, only supervised learning, let's look at the following. The case of linear regression or regression. In this case, is for linear regression, which should be familiar to you, just using linear models such as mx plus c to make a prediction. And in this case, we're using a model to do classification. And this model is based on something called decision trees. And this is an example I made up for credit card scores. So in this example, you have 3 descriptors: the age, whether the person is a student or not, and their credit card rating status. And to make a prediction, you go through this list of descriptors and through each node, and you say, for instance, what is the person's age? If they're young, you ask, is the person a student? If they're not a student, you don't give them a credit card. And if they are a student, then you do give them a credit card. And you can apply this to other areas, of course, such as housing prices, or of course, areas in physics. So this is regression models and classification models. So more on regression, diving a little bit deeper, you have a one-dimensional data, and keep in mind, the advantage here is that you can use this same technique for very high-dimensional data for hundreds or thousands of dimensions. For the one-dimensional case, you can really easily see that, okay, what could this fit is maybe a line, and then you can perhaps try to use a line or first-degree polynomial or perhaps a second-degree polynomial, and to try to make a fit. And to be able to figure out which model you should use, which degree polynomial you should use, there is a model validation process. There are many examples of this. The example I show here is for something called k-fold cross-validation. And in this case, I have 5 folds where I take my training data and divide it into 5 bits. And I use 4/5 of those data for training. And then the last bit I use to kind of estimate the score, how well the model performs. And I repeat this 5 times, shuffling data around each time, and I get the average performance. And I do this again for a different model. And so in this case, I can consider mx plus c. In another case, I can consider a parabola. In another case, I can consider a third-degree polynomial. And by doing this model validation process on just the training data shown here, I then select which model is the best for me. And in the language of machine learning, you find that you find the best hyperparameters for the model. And after you do that carefully, let's say the linear model is indeed the best. You have this line representing your model fit. And in the end, then you bring in the test data, which is the data that the model hasn't seen at all. In this case, when all is said and done, model behaves really well, and it gets 1 point almost perfectly, and the area here is pretty small, and the area here is pretty small. So that's a very simple example for linear regression for a one-dimensional case. Let's move on to classification. And let's make this a bit more physics inspired. So let's consider some data involving ferromagnetism in ordered binary transitional metal alloys. And let's plot a two-dimensional descriptor space. On the x-axis, I'm plotting the available atomic volume. On the y-axis, I'm plotting the calculated chemical hardness, which goes like d mu dn. And I'm labeling my data in 2 ways. An alloy can either be non-magnetic, which are the black squares, or ferromagnetic, which are the open squares. And we notice if you look at these data carefully, that there's a region where they're only ferromagnetic samples. So by looking at the pattern in the data, there's a new point that falls in this region of the two-dimensional descriptor space. We know right away that this thing should be a non-magnetic. However, if there's a point that falls here in our descriptor space, we can guess right away that it should be ferromagnetic. So this is really a ripe case for a nice case for using machine learning, where you have a well-defined descriptor space, and we can make a rule for finding whether something should be ferromagnetic or not. And for this case, we can use a decision tree, which is, as I explained before, has descriptors at each node. And for descriptor 1, we can say if it's less than some value v1 or greater than value v1, we can, for instance, go to descriptor 2. And if that descriptor 2 is less than value v2, or greater than some value v2, we can label something to be either non-magnetic or ferromagnetic. And I'll give us the specific case. This is a general case. And the specific case for the data we have here, there are only 2 descriptors. There's this two-dimensional space, right? There's chemical hardness, and there's atomic volume. And then for this case, if the hardness is greater than 0.25, we can label it to be, excuse me, non-magnetic. And if it's less than 0.25, we can label it to be, we can go to the next node and then ask the question, is it less than some value? If it is, then it's ferromagnetic. If it's greater than some value, then it's labeled to be non-magnetic. And actually, this has a very, very high prediction accuracy for this model for these data. So it works really, really well. That's an example for classification. But I haven't thought about something really important, which is called overfitting. To illustrate what overfitting it means, it's an important part of machine learning, and it really kind of boils down to not trying to fit the noise in a particular data set. So I'm plotting data here, which is identical in the left, middle, and the right panel. I'm making different fits each panel. Now on the left side, I have a linear fit, and you can see that the model doesn't really capture all the variability in the data, and it does what people say, what is known as underfits the data. On the right side, the model is capturing all the variance in the data, perhaps too well. It's capturing so much it's actually fitting to the noise, and that's what people call overfitting. But what you want is really a case where you're in between these two regimes. You're in a Goldilocks zone where you're having enough variance to really capture the underlying behavior of the data, but not so much that you're fitting to the noise. And in this case, it's just right. In order to not overfit data, people employ several tools, and one of them is called regularization. Or again, the goal is you have some observable quantity y. You're trying to build a model f of x that kind of matches this quantity y without having it be affected by epsilon or the error. And typically, what one does is puts constraints on the coefficients of a model. An example of that is lasso, which is linear regression with constraints. Or over here, you have the linear regression piece. That's x beta, where y is the measured data or the observed data. And so this is just the linear regression bit. And over here is the lasso bit, or the regularization bit, where lambda is equal to 0, you recover vanilla linear regression. Where lambda is large, you tend to put constraints on these coefficients beta. Or in the case here, the coefficients are called theta. And if the constraint is high for the theta, then you have theta 4 and theta sub 3 going close to 0. So in the end, you recover this case, which is the case you want to really capture the behavior of the data just right without fitting to the noise. Another thing people do for the case of neural networks is something called a dropout, where they kill some of the nodes in the neural network to reduce the number of coefficients or parameters in the model to have regularization. So far, what we've done is chosen some models that are trying to capture the behavior of some underlying system without fitting too much to the noise, to very quickly predict some values without having to do experiments or new calculations. And it turns out that neural networks are well known to be universal functional approximators. So they're of great interest to the physics community or anyone wanting to build some model to predict something without having knowledge in advance of what the behavior should be. So let's take some time to talk about neural networks. Now, so what is a neural network? It's essentially consisting of input nodes and output nodes with also a hidden layer with this form where the inputs are x's. The hidden layers is described by z's, and the z1, and output layer is z2, where you go from inputs to the outputs through doing this calculation. These are like doing a linear calculation. But the neural networks are made nonlinear through these G's here, which is any nonlinear model. And these things are called the activation function. So for a concrete case, for the case of predicting the housing prices with some inputs, the size of the house, number of bedrooms, zip code, and wealth and, of the person, so on, where these are the inputs, you pass it through a hidden layer, and you get to an output using these expressions. And in this case, the activation function, which again is any nonlinear function, or can be any nonlinear function, is described by a sigmoid, which is shown here. Turns out these work really well and are really good for predicting the housing prices given sufficient quantities of data. And I've recently applied to study physical systems, which I'll talk about in a bit. Now, there are different architectures one can construct for neural networks. The simplest one is called a perceptron with no hidden layers. The one we just talked about is called a feed-forward neural network. There's also examples which are kind of popular these days, are deep neural networks with many hidden layers, which can be many layers deep and also quite wide. There's also something called autoencoder and the recurrent neural network, which have unique uses and are quite effective for the areas of research that you might want to apply them to. Recently, physicists such as Marius Mathiakis, Pavlos Protopapas, and Euthymios Kaxiris at Harvard are interested in tuning the architecture of the neural network to embed in it physical principles. And the graph, or the view graph I'm showing here, is a case where they want to constrain the consymmetry of a function to be either odd symmetric or even symmetric. So they have a neural network and they say, well, I know that the result in the end is going to be even symmetric, and they tune the symmetry, tune the constraints such that the result has to be even symmetric. This is one way to regularize the function, and it's another way to embed in physics, and they can also embed physics like energy conservation. So the other examples where they're trying to train a neural network to solve a differential equation, and they can constrain it such that the energy has to be conserved. And if they do that, the neural network is more easily trained. And once it's trained, has a higher prediction accuracy. It's really quite impressive. And please see this paper for more information. Now, I've kind of gone through really quickly how one can do data science, and I'll apply it to an area which I was interested in when I first started. So let's look at this case study of data science for materials research, and that is applied to magnetic 2D crystals. So let's consider a 2D magnetic material, chromium germanium telluride, which is known to be ferromagnetic, and consider chromium silicon telluride, which is known to be anti-ferromagnetic. And the difference here is just between this one and this one is that you replace germanium with silicon. So by changing the atomic, or rather the crystal structure, the atomic composition, you can change the magnetic order. This is the crystal structure for chromium germanium telluride, where chromium are the A sites, germanium the B sites, and tellurium the X sites. So by tuning the composition or the identity of A, B, and X, you can tune the resulting magnetic properties. So this is what I tried to do. I made very many decorations of this crystal structure archetype, labeled it differently with different atoms for A, B, and X, and I calculated its magnetic properties. And if you do that using density functional theory calculation, you get the following, where A site substitutions are on the vertical axis, the B site substitutions are on the horizontal axis, and the X site substitutions are on the panels, so here, here, and here, and the color represents a magnetic moment. And just keep in mind here that, notice here that there is some pattern in the data, which you can kind of tell there's a pattern. Maybe it's difficult for the human eye to quantify it, but the hope is that the machine learning model can learn what the pattern is and exploit it to predict many other ABX3 structures. So it took me 6 months to generate these data. And in the end, I built a machine learning model to learn what the pattern is here. And you can get, and these are about 200 structures. Total number of ABX3 combinations are about like 10 to the 4. And so I can exploit the search of this space by building a model, and that's what I did. And this is the calculated magnetic moment on the x-axis. This is the predicted magnetic moment on the y-axis. This dashed line is just a guide to the eye, showing that the training data and the test data for this model are quite good. The model's working quite well, and I can extract out descriptors for the behavior of this decision tree based model. And this shows that the the mean number of spin-up electrons, or the number of unpaired electrons, is the most important model or descriptor for making this model successful. And if you know how magnetism works, this is not surprising, but it's also a good reality check. So by combining our descriptors and building a model, we can then make some machine learning predictions, which I do here for the next moment, and something called formation energy, which is a proxy for whether the crystal could actually stay together or not, whether it can be made in the lab or not. And this is a subset of about 5,000 calculations or predictions that I made. And we can then go through and select the best predictions, verify with first principles calculations, and eventually, hopefully, we'll do this in some months, make it in a lab to show that this whole process works. So this is just an example of the data science process and how I applied it when I first got started. So who can do data science? Well, it's known that programmers are good candidates for becoming data scientists. Data wranglers are also good candidates. In addition to computer scientists and mathematicians, and of course statisticians, and of course physicists. And this is you beginning your journey as a data scientist. Some resources to help you on your journey are shown in the following slide. Resources for self-learning include Coursera. I listened to this, I took this class by Andrew Ng called Machine Learning when I first got started. It's a wonderful course. I suggest you take it if you haven't already. There's this book by Trevor Hasty called Introduction to Statistical Learning, which is a wonderful book. It explains all these ideas much better than I just did, and very clearly and really nicely. The C-Tree newsletter is giving you examples of more materials research plus machine learning papers, and it's also a good resource to understanding more about how you can apply machine learning or data science for materials research. Good workshops to attend are the IPAM at UCLA, and that's the Institute for Period Applied Math, and the Institute for Applied Computational Sciences at Harvard has a Compute Fest each January, where they give a whole week-long courses in how to do deep learning or machine learning. It's a really nice class, a really nice workshop. For accessing data to get started, to play with data science models, you can use Kaggle. You can use Google's dataset search. There's also materials data available from C-Tree and the Materialist Project, to name a few. And data science tools we should become familiar with include Jupyter Notebook, Scikit-learn, TensorFlow, Keras, and PyTorch. The last three are for more deep learning things. And for information, please visit materialsintelligence.com for a detailed list of resources. So very quickly, an outlook. There's a growing interest in data science. Google and Facebook are seeking collaboration with the physicists, not just because they want to do physics, but they see that physicists can contribute to improving models in machine learning and AI. And there's also interest in, as you've seen, in creating machine learning models which have embedded in them physical principles, and using AI not just to predict things through some black box model, but also understand underlying physical principles, using AI to understand physics. This is again, here's my webpage for a link to more valuable resources. You can either go to the page or use this QR code to access it directly. Thank you.
Thank you so much, Trevor. I think that was a really nice outlook of data science and tools, and as well as your research. It's very interesting. So if anybody wants to ask any questions, there's a questions box. I already see a couple of questions. So let me ask the first question. First of all, data science, given all these libraries, how important is coding skills, given that all of these libraries exist?
Coding is along with good coding practices, is still very important. The nice thing about all the libraries is that you don't need to, for instance, build a linear regression model from scratch, or you don't need to build a neural network from scratch, because the libraries exist. So it speeds up how quickly you're productive. But again, good coding practices are still very important because you need to be able to kind of massage the data, first import data from your data set. Even if it's just a CSV file, you have to be able to transform that data into a form that's useful for your model. And it may be like just a bunch of images from a website. You need to be able to take those images and parse it into a form that your model can understand. So coding is still a very, very important skill.
Another person's asking about, will some of these information from the webinar be available? I'm just going to answer that question for everybody. We will be posting the video from this webinar at a later point, so everybody who has attended will automatically get that resource. Okay, the next question is machine learning faster than DFT?
Well, so you can evaluate the machine learning algorithm in milliseconds, and it may take DFT of some minutes up to several hours or days to do a calculation, depending on how complex it is. So if you have a trained machine learning model, I think for most cases, it'll be much faster than a DFT calculation, yes.
Okay, what guides the appropriate structure, for example, the depth and width of a neural network for a particular application?
Yeah, that's a great question. That's an open research question, and there's no hard and fast rule for how to do that. And typically, what people do is they play around for some weeks or months on trying different things, the width or the depth of the neural network. And after playing around, they have some idea of what works well for a particular problem. And if they have a new problem that they haven't tackled before, they may try what they've done before and kind of go from there. But it's really an open research question how to tune your architecture, and depending on how you choose your architecture, the thing you're trying to solve, the target really varies quite widely. But that's a great question.
Okay, and then another question, and do you have concrete examples on how to incorporate physics principles? I guess they mean in the context of machine learning.
Yeah. So the example I alluded to here, the work by Maris Mathiakis and Ximios Kexiras, and in the example here, this is not the related graph, but they have another paper which they're trying to solve a differential equation. And so there are many differential equations that arise in physics, and they impose energy conservation in their solution. And this is one example where you embed physical principles into machine learning models. In a more simple-minded sense, in my example here, I skipped this step, but I started from my data set, right? My DFT data that are shown here. And before building my model, I showed the result here, but I had to choose which descriptors I would use. And I skipped this step, but I showed the results of the most important 6. And I had to input this into my model. So I have to know about magnetism, and I have to know that the number of unpaired electrons should be important in predicting magnetism or the magnetic moment. And I include it in my result. So you still have to, in this sense, you can add a descriptor that is describing the thing you're interested in. And there are other ways to do that. And indeed, descriptor development is an active area of research. And if you go to this website, you'll find some more tools or more ways to consider how one might do that. For instance, if you're looking at the crystal structure, you can embed physics into this description of crystal structure in order to do machine learning of different either molecules or 3D materials.
All right, well, thank you so much. And so I want to thank both the speakers. And like I said, all the information will be available online, and we'll be sending a follow-up. In the meantime, please, if you're available, you can attend the next webinar, which happens at 3 o'clock, as well as stay posted for future webinars. And thank you so much for helping us. I want to thank all the speakers, as well as attendees and all the other organizations for helping make this a success given the recent events. Thank you.
All right, bye everyone.